Okay, at this point, we're going to proceed to watch a video which will give us an overview of how to use a hemocytometer to determine a cell count and also how to determine cell viability, both of which will be useful for the practical write-up. Okay.
In this video, you'll see how to use a hemocytometer to get an accurate cell count and how to convert this data into usable cell density and viability information. The hemocytometer was originally developed for counting blood cells. Today, it is used to count many other cell types as well. A hemocytometer consists of a special glass microscope slide that contains two separate counting chambers. Each chamber is etched with a carefully crafted grid with exact dimensions. There are two supports on either side of the counting chamber. When a cover glass is placed on the supports, the depth of the chamber will be exactly 0.1 millimeters. Now we know both the area and the depth of the counting chamber, and we can calculate the volume. We can also use the grid to count the number of cells in each section and calculate the cell density. Before you start, you need to dilute your cell suspension in trypan blue solution, which is used to stain any dead cells present in your sample. Make sure your sample is mixed well. Counts should be within 2 minutes of incubation with trypan blue. Be sure not to wait more than 5 minutes, as longer incubations will result in trypan blue entering live cells. A dilution factor between 2 and 10 usually works well for mammalian cells. To get accurate cell counts, it is recommended to have no fewer than 10 and no more than 50 cells over each square millimeter. Basically, you don't want to be counting 100 or 200 cells per square. You want to use appropriate dilutions to get 10 to 50 cells per square. Make sure the hemocytometer and cover slip is clean. 70% ethanol can be used for the cleaning. Carefully place the cover slip on the supports using gentle pressure and small circular motions. Here's a tip: moisten the shoulders of the hemocytometer before you fix the cover slip. Make sure your diluted cell sample is mixed well and load 10 microliters by gently resting the end of the pipette tip at the edge of the chamber or the edge of the cover slip. Do not overfill the chamber. Let the liquid be drawn out of the tip and fill the counting chamber by capillary action. With a microscope and a 10 times magnification, you will be able to see approximately 1 square per viewing window. Use phase contrast to distinguish the cells. Live cells will not be stained by trypan blue and will appear white, while any dead cells will be faint or dark blue. Now you can count all the cells that fall within a couple of the larger squares and include any cells on the right hand or bottom boundary line. Count the number of live cells and dead cells. A good suggestion could be to count the cells in squares 1, 3, 5, 7 and 9. Obviously, the more squares you count, the more accurate your cell count will be. Just remember how many squares you counted. Did you know there's an app you can use for this? The Cell Culture app has a cell counter tool that will help you keep track of life. Based on the number of viable and dead cells, you can now calculate the cell viability. To calculate the density of the viable cells, you need to determine the number of live cells in a particular volume. This volume is defined by the number of squares that you counted and the volume of one such square. We also multiply by the dilution factor in order to determine the cell density of your original cell solution prior to diluting with trypan blue solution. The hemocytometer is designed so that the volume of each of the largest squares is constant. Each square will hold a number of cells equivalent to the number of cells counted multiplied by 10 to the power 4 per milliliter. To convert, we then calculate the density of viable cells by looking at the number of live cells multiplied by 10 to the power 4 per milliliter, the number of squares counted, and the dilution factor. The hemocytometer and these equations helped us determine cell density and viability. Based on this, you can also create growth curves or calculate the best window for cell passaging. You'll find more information on how to perform these basic cell culture calculations in a separate video.
So now we're going to deal with the issue of calculating the volume of cells that is needed in order to fulfill the request that Emer has asked for. So, for instance, if Emer had asked to provide 2 mils of 5 by 10 to the 5 cells per mil, you need to work out the total number of cells that are required. Okay. Say, for instance, the cell count you obtained was 45 by 10 to the 4. Then in order to work out how many cells we need to achieve 2 mils of cells at 5 by 10 to the 5, we need to follow the 3 steps that we're about to cover. Okay, so step 1 is, what is the total number of cells required? Okay, and the equation for that is volume of cells required, multiplied by cell concentration desired. Okay, in this case, we've been asked to provide 2 mils at 5 by 10 to the 5 cells per mil. And when you do that calculation, it tells us that we need 10 by 10 to the 5 cells in total, or another way of expressing it would be 1 by 10 to the 6. Okay? Therefore, in order to obtain 2 mils at 5 by 10 to the 5, we're going to need 1 by 10 to the 6 cells. Okay, so we now know the number of cells required for that. Step 2. How much of my cell solution do I need to obtain 1 by 10 to the 6 cells? So at this step, you're trying to work out how much of the cell solution obtained from Emer do you need to obtain 1 by 10 to the 6 cells. And the way to do this is cell number required divided by cell count obtained. So the cell number required is 1 by 10 to the 6, and the cell count obtained was 45 by 10 to the 4, or 4.5 by 10 to the 5, whatever way you want to express it. Okay, but the easiest way to do this calculation is to make sure that the cell number required and the cell count obtained are in the same units. Okay, so I've transformed both of these to 10 to the 4. So it's 100 by 10 to the 4 divided by 45 by 10 to the 4. So it's 100 divided by 45, which means the answer is we need 2.222 mils of cells that we obtained from Emer to obtain 1 by 10 to the 6 cells in total. Okay. Step 3. Remove the 2.222 mils of cells, place them into a centrifuge tube, centrifuge them, remove the supernatant, and when you remove the supernatant, at the bottom of the tube you'll have the pelleted cells. And with the pelleted cells at the bottom of the tube, simply add 2 mils of buffer to resuspend the cells. And what you then have is 2 mils of buffer containing 1 by 10 to the 6 cells in total. And because it's in 2 mils, the concentration then is 5 by 10 to the 5. So that's how you go about doing a cell count and working out the volume of cells that you need to achieve a given concentration. Okay. So in terms of what you're being asked to do in relation to task 1 for assignment 2, task 1 of the assignment will provide you with a hemacytometer screenshot. And we're asking you to use that screenshot to undertake a cell count. Okay, so you undertake a cell count using the screenshot. And what I'm asking you to do is to determine the percentage cell viability. I'll also ask you to calculate the volume of cell solution provided by Emer that will be required to obtain enough cells for an experiment. Okay. For example, You will be asked to determine the volume of the cell solution provided by EMER that would be required to obtain a solution of 2 mils at 10 by 10 to the 5 cells per mil. Okay, and that part of the assignment will be worth 20 marks. Okay, and you'll find this in the answer book. So that's task 1. Task 2 is focused on flow cytometry. Okay, and it will involve HIV patients. So you'll be provided with blood results from 3 patients. Okay, you have been asked to quantify the absolute number of CD4 cells and CD8 cells. And this information will be used to provide an indication of the severity of the HIV condition. Okay. And in terms of what would happen practically, you would add an antibody mix to the blood to enable cell markers specific to CD8 and CD4 cells to enable identification of these cells. The antibody-labeled blood will be analysed using the flow cytometer to enable the absolute number of CD4 and CD8 cells per mil of blood to be quantified. You will then be provided Okay, for task 2, it will be focused on flow cytometry. You'll be provided with blood from 3 HIV patients, and you'll be asked to quantify the absolute number of CD4 cells and CD8 cells, and from this provide an indication of HIV severity. What's involved is the clinician would obtain a blood sample from the patient. They would then add an antibody mix to the blood to enable them to identify a range of cell markers that would allow them to identify CD4 and CD8 cells. The antibody-labeled blood will then subsequently be analysed using a flow cytometer, and that will enable us to quantify the absolute number of CD4 and CD8 cells per microliter of blood. And you'll also be asked to calculate the ratio of CD4 to CD8, because this is also important in the clinical decision. Now, there's a lot more information on the background to the flow cytometer in the presentation provided on BabyLearn and on the link on this presentation. So from a practical point of view, what would happen is, as I said, the clinician would obtain the blood tube. They would have 50 microliters of conjugated antibody to a true count tube. They would then add 50 microliters of, start again. Okay, in terms of the procedure, the clinician would take a specialized tube called a true count tube, which contains in it counting beads, which we'll cover shortly. So they would take this true count tube and they would add 50 microliters of antibody. They would then subsequently add 50 microliters of patient's heparinized blood sampled to a true count tube. And after that, they would add 900 microliters of BD lysine solution to a true count tube. They would subsequently vortex the mixture, let it incubate in the dark for 5 minutes, and after that, the blood sample is ready to be analysed on the flow cytometry machine. So, in terms of determining the volume of blood used, this is an important factor we need to consider because determining the volume of blood that's been used by the flow cytometer is critical to establishing the amount of CD4 and CD8 cells per volume of blood, and to enable us to compare to guidelines that are provided on this. So, flow cytometer itself takes up blood for analysis, But the difficulty is that when the flow cytometer takes up the blood for the analysis, there's no way of determining what volume was taken up by the machine. So this creates a problem because the clinical decision needs to be based on how many CD4, CD8 cells there are per microliter of blood. So, as I said, we need to determine the volume of blood used by the flow cytometer. Well, how do we do that? We're able to quantify the volume of blood used by the machine by spiking the blood with a known number of true count beads. Okay? These true count beads have fluorescent properties that enable the flow cytometer to detect them. So, for instance, if we spike 1 ml of blood with 1 million beads, okay, so the patient blood now contains 1 million beads. If the flow cytometer detects 500,000 beads when the sample is analysed, then we can establish what volume was used by the flow cytometer. In basic terms, if 1 ml of blood contained 1 million beads and the flow cytometer detected 500,000, then on that basis we can allude to the fact that most likely 0.5 mils of the blood sample was used by the flow cytometer. And that's the basic principle for the true count beads. They're fluorescent beads that are spiked in the blood, and the flow cytometer then detects the amount of these fluorescent bloods that's taken into the machine, and indirectly then we can work out the volume of blood that was used by the flow cytometer. So what I've tried to do here then is provide you the step-by-step procedure for calculating the actual number of CD4 and CD8 cells present in the blood to enable you to make clinical decisions. Okay, so the calculation, you need to calculate the volume of liquid or blood taken from the true count tubes by the flow cytometer in order to determine an absolute number of CD4 and CD8 cells. And as I said before, this is achieved by true count beads. Now folks, as I noted earlier at the start of the presentation, in order to get the true number of cells in blood, you need to take account of dilution factors. Okay, so the blood was mixed with antibody and mixed with lysine solution. So you need to take that into account at the final calculation, okay, for the dilution factor. So, in order to work out how many beads per microliter or how many bead counts per microliter of bead solution in tube, it's a total number of beads divided by the final volume, okay? And then the volume used by the machine, the calculation for that is the bead count that the machine has detected divided by the bead count per microliter, okay, which you've calculated just above. Okay, so that will give you an indication of the volume used. So now, in terms of absolute count, you will be provided with results and you'll be asked to subsequently determine the absolute count. And the absolute count will be the gated cell count on the flow cytometer, okay, the number the number of cells that the results report, divided by the volume used, okay. And then, as I said before, once you have that absolute count, you need to adjust for the dilution factor. So the absolute count multiplied by the initial dilution factor will let us know the actual number of cells per microliter of blood. And of course, as I said previously, another important factor to consider is the CD4 to CD8 ratio. Okay, so CD4 to CD8 ratio will enable us to determine how sick these individuals are. And there's a worked example in the notes provided that have been provided alongside this presentation. that will enable you to undertake these calculations. Okay, folks, so that's just a basic introduction in relation to what is expected from you in relation to this assignment or practical. So in terms of tips and advice, take the time to view the presentation on the theory of the flow cytometer, and also read the associated documents to help you with this assignment. It's an assignment, therefore you have to invest time to do some background reading. At every stage that involves calculation, always remember to consider dilution factors. And like any calculation, it's important to show all you're working out, each step of your working out, in order for you to achieve maximum marks. Another tip is be careful with plagiarism. If cases of plagiarism will be detected, they've been detected before and will be detected again. And if plagiarism is detected, then you will be required to undertake a plagiarism interview, and any component that was plagiarized will not be marked. So if you plagiarize, you will not receive a mark, and you'll have to resit with a cap at 40%. So take care with plagiarism. And lastly, if there's any clarity needed on any aspect of the presentation or the practical, please don't hesitate to contact me. I'm more than happy to have a Blackboard Learn Collaborate Ultra discussion if that's needed in order to provide some clarity on that. Aside of that, folks, it's not the most ideal way to get introduced, but I really look forward to interacting with you in relation to this module and this assignment. Thank you very much.